Welcome to the second of our two-part lecture on alternate actuation. This lesson focuses on shape memory alloy and piezoelectric actuators. Along with electromagnetics, such as the different type of motors we've discussed, there are other transducers available for interaction between our mechatronic systems and the environment in which these systems are operating. An example of such a transducer uses thermal energy. Consider here a block of material, and by some means I heat up the material. So maybe I run a current through the material and heat it up as if it were a resistive heater. As this material heats up, it will expand. This expansion will result in a thermal strain equal to alpha times the change in temperature. Alpha here is the coefficient of thermal expansion. Sometimes you'll also hear this referred to as CTE. And as an example of a common material, the CTE of a common material, let's consider aluminum. Aluminum has a CTE of 23 times 10 to the minus 6 meters per meter, or 26 microstrain per degree C. So this approach to heating a chunk of material, it typically has a relatively small effect in terms of creating a displacement in the environment. However, one means to exaggerate this effect is that instead of using a material like copper or aluminum or silicon, we could use a shape-changing material or a shape memory alloy, such as a nickel-titanium alloy. So for a shape memory alloy, or an SMA for short, a change in temperature imparted on the alloy results in a phase change of the alloy. At low temperatures, we have what's referred to as the Martensite phase. And there are two versions of this phase. We have this undeformed version that looks like this. So we have the structure of the atoms in the alloy, and if we deform that alloy at low temperature, it'll look something like this. And at higher temperatures, everything straightens out, and this is referred to as the austenite phase. So from subjecting the material from a low temperature to a high temperature, we create a strain in the material that's not necessarily due to the change in temperature. It's actually due to a phase change in the alloy. In other words, the atomic structure of the material is changing. As we mentioned, a great way to heat up these SMAs is to run a current through the SMA and use it as a resistive heater, where the power through the resistor goes as I squared times R. And thus we can think of the change of heat with respect to time, Q dot, going through this material as proportional to I squared times R. SMAs have some great advantages. One of the primary advantages is the amount of power or force generated per unit mass of alloy. So we could think of these as specific power or specific force for a particular actuator. SMAs are very often used for mechatronic systems where mass is fundamentally limited. So something like a UAV would be a great application for an SMA. SMAs are also relatively simple to use. All we really effectively need is to run a current through the SMA to generate heat. And this heat will then switch the SMA between phase states, so from Martensite to austenite. In terms of disadvantages of SMAs, the primary disadvantage is going to be efficiency. Ultimately, we're going to waste a significant amount of energy by heating the SMA. SMAs are typically bandwidth limited. We are unable to actuate the SMA very quickly. They won't move very fast. And in some cases, displacement can be a disadvantage as well. Going from our Martensite phase to austenite phase, we're typically looking at about a 3 to 5% strain, which is a reasonable amount of strain, but typically less than something we get with an electromagnetic actuator like a solenoid. So let's take a look then at how we would use an SMA. The first step in using an SMA is to train the SMA into the shape with which you ultimately want to use the SMA. And you can also think of this as the shape memory portion of the SMA. This process typically occurs at high temperatures, so somewhere on the order of 550 degrees C. So as an example, let's say we've trained an SMA into a straight line geometry as shown here. The second step will be to reduce the temperature below this annealed step at 550 degrees C down to the twinned Martensite phase. We'll then add a mechanical load to the SMA to strain the SMA. And at this point, we'll be in the deformed Martensite phase with a strain on the order of about 5%. Next, we'll heat the SMA, typically by running a current through the SMA. This will return the SMA to its memorized shape, or effectively put the SMA back into an austenite phase. We'll then go back and forth between these steps, from the deformed martensite phase to the austenite phase, and move this mass up and down. So this is a relatively simple but typical use case for an SMA. In addition to SMAs, another common alternate actuator for mechatronic systems are piezo electrics. Piezoelectric materials can either generate an electric field when they're deformed, and this is what's referred to as the direct piezoelectric effect, which is very important for sensing. So for example, using this as a pressure sensor or a strain sensor, or they can deform under an applied field. This is what's referred to as the indirect piezoelectric effect and is utilized for actuation. A unique aspect of piezoelectric materials is the presence of these dipoles. And these dipoles will tend to orient themselves in the same direction when the material is pulled. When we close the switch, we'll get a displacement and create a stress and strain in the material. In this circuit, we have positive charges coming out of the supply with negative charges on the other side, so these charges will tend to squeeze and compress these dipoles, thus squeezing and compressing the piezoelectric material. Piezoelectric materials, they can provide a lot of stress, although typically a smaller amount of strain, even smaller than an SMA. They also typically require a relatively large electric field, so very high voltage, somewhere on the order of a couple hundred volts. But they are fairly easy to construct and fairly affordable, and this is why you see piezoelectrics popping up in things like buzzers in your Arduino parts kit. Piezoelectrics are also being used in various research applications, such as microrobotics for deformable walking legs for microrobotics, as well as opening and closing valves.